The first thing I like to do is find the mean of this distribution. So just like we've done in the past, I'm going to symbolize this. And the mean of this distribution, the theoretical mean, is take the probability of getting 70 and multiply it. The probability of getting 5 and multiply it by that quantity. And the probability of getting -10 and multiply it by that quantity. And here we have the mean. Since we're interested in showing what bias means in terms of the sampling distribution, let's create a scenario where we're going to sample 3 times from this distribution. And we're going to create the theoretical sampling distribution of the following. Sample 3 times, and after I sample 3 times, what I'll do is find the average of these 3 numbers. So I'm after that distribution. To we do this, I will first look at taking 2 possibilities, 2, and seeing what kind of result. So for example, if I randomly select 2 values, I can get 70 and 70. When I add them together, I get 140. Or I can get 5 and 70. When I add those together, I get 75, and so on. This is the result of all the possibilities. And because it's a game of chance, and I have independence every time one draw occurs, I will put the card back, shuffle, and it's like starting from scratch. So these probabilities hold after every single draw. If that's the case, then I have independence, and to find out, for example, the chance of getting 140 to appear, all I have to do is take the chance of getting 70 is 10%, and the chance of getting 70 is 10%, multiply, and I get this value. The chance of getting 270 draws is 1%. So now I take these possibilities along with these values. So for example, 140 only occurs once, so that's the probability of that. While 75 occurs in 2 places, I have to take each individual probability and add them up, and so on. The result, it's this probability you see right here. And notice when I add all the probabilities, I get 1. So this is my distribution of 2, just sampling twice. But I want to sample 3 times, so we're going to do this again. To find the next set of possible results, I'll take this table, which contains all possibilities of 2, and combine it with one more card for my third draw. So again, all I'm doing is summing right now. So 140 is one possible sum of 2, plus my third card, 70, gives me 210. The chance of that happening is, well, the chance of 140 is 0.01, the chance of getting 70 is 0.1, multiply them together, and this is my chance of getting 140. And I'll do that throughout again. I have independence, like I said before, and the result is this table you see right here, where you're summing 3 possible outcomes. So a sum of 210 is possible, a sum of 145, and a sum of 130. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only 10 possible outcomes. There's no more. So it's a finite set. To find the average, really, all I have to do is take all these values and divide them by 3. So now I'm going to do that. Here's 210. All I need to do is take 210 and divide this by 3. Oops. And I get 70. As a matter of fact, I'm going to do this automatically. I'm just going to tell the computer to look here at the previous table and divide that by 3. then I will perform that same operation to all of them. And now these are my averages. Each one of these is X bar. So the reality is, what you're looking at is X bar for a sample of 3. This is a possible outcome, this is a possible outcome, this is a possible outcome, this is a possible outcome. To show this is the case, I'm going to just generate a few data values here. So I'm going to use Excel's random number generator. I'm using data analysis. It's off screen. It's in the data tab if it's available. Create 3 columns. Actually, I'm just going to do this 10 times. The distribution is discrete. Go get it. I'll highlight my numbers. Actually, it likes this vertical. Let me stop here and align everything vertical. I've now aligned everything vertically. I'm just going to highlight the data. This is my parameters, the outcomes, and the chance of those outcomes. Random seed is anything you want. I'm going to place my output right here. And here I have 3 columns, all representing different things that could have happened. So for example, if I average these 3 numbers, I get this value. I'm going to average the rest of these numbers. Looks like 16 and 2/3 is a very likely outcome. And when I come down here, this is the number I got several times, 16 and 2/3 as one of the possibilities with a 19% chance. So it's no wonder that that appeared quite often. If you look at the probabilities for these other outcomes, 16 and 2/3 is a very likely outcome. And what was the other number I got? -10. And -10 has a 51% chance of occurring. So again, a very likely outcome. So the 2 most likely outcomes is what I experienced. But of course, what I want is the mean. We're going to talk about bias. So bias has to do not with these individual outcomes, but it's about all possible individual outcomes. So you cannot talk about singularities like this. You have to talk about everything. And this table represents everything that can happen. So now to find E of X bar, all I need to do, the mean X bar is again take this value, its outcome of 70, times its probability, and I'm going to do that same procedure to everything here. Finally, what I want to do is sum everything up. So I'll come over here to the home button, click on auto sum, and it will sum everything for me. And notice that I'm getting the same value as I got previously, -0.5. So I can see that E of X bar is equal to E of X. That's very same distribution I'm sampling from. So the question becomes, how did that happen? The answer is simple and has to do with bias. And now we can talk about what bias means in this context. Bias just means that you're going to favor one thing more than the other going against the proportions that appear in the population. So for example, my population in this scenario has only three possible outcomes: a 70, a 5, and a -10. There's nothing else. The 70 occurs with 10% chance or frequency. 5 appears with 10% frequency, and the -10 appears with 80% frequency. So -10 is something that appears most often. Bias just means that somehow this is going to get altered. And how could that possibly get altered? Well, if you sample incorrectly or sample in a way that's not considered acceptable, that will in the long run generate unbiased or representative results, then you cannot expect these numbers to align. It doesn't mean that my sample will have exactly 10% 70s, nor 10% 5s, nor 8%, 80% -10s. Here's what we're saying. When we're in a bias sampling situation, what we're saying is that we're sampling in such a way that 70 doesn't occur 10% of the time, nor does 5 occur 10% of the time, nor does -10 occur 80% of the time. Somehow they've been altered. So let's say that, for example, you, for some reason, are playing this game and you think you're doing it according to these rules, but in a way, you're not playing really according to these rules. In other words, you're biasing, so these proportions are not going to come out exactly correct. So, for example, let's say that I come over here and while 70 only occurs 10% of the time, you're doing it in such a way, or maybe somebody has figured out a way to alter these probabilities, like a gambler that has created a system, right? You hear gamblers come up with a system. Well, in that case, they're circumventing random chance, just pure random chance. That means that, let's say they figured it out, that they can ratchet this one up. Um, they can they've come up with a system and says, look, 70, I can get this to come out 30% of the time, right? And what about 5? Because, well, I figured out also through this system, and I can make that occur 20% of the time. So that leaves, of course, the -10, that if you're the casino owner, you would like this to appear most of the time. Now there's only a 50% chance of this one occurring. So in that scenario, as a matter of fact, let me alter this a little bit and make it a little more in the casino's favor. 336. No, that's really bad. Sorry. Let me alter this one more time here. Let's say I get this to 70. Let's just twist this a little bit. Not too. I don't want to get this too bad off, but you're done this. Something like this. Leave that at 10 and up this to 0.2. Now, when I calculate the mean, so you've altered the probabilities a little bit. You've created 70 to appear more often. Then all of a sudden, I have the following situation. What is the mean of this distribution? Now the mean is 7.5. So you notice a tiny alteration in the frequency has caused the mean to change, in this case drastically, because 70 is such a outlier. So just this change from 10% to 20% has caused a big change in the mean. So now, as a gambler, you're favored. You're favored to win. What happens when I actually play this game? You'll notice when I actually play this game, if I only played it 1, 2, 3, 4, 5, it's hard to see that. I mean, will the numbers look drastically different? I don't know. Let's find out right now. I'm going to grab another sample. But but this time it's going to be from this distribution, the biased one. And I'm going to put these outcomes here in A23. And all I'm going to do is find the averages. Now you'll notice things have been altered now. This number, 21, is appearing more. 21 appeared again here, negative 10, 70 appeared. Notice it didn't appear here. So what's happening is by the time I get done, this is going to, while these outcomes are identical, those are not changing. The frequency at which they're happening is changing. And that's all we mean by bias. If our sampling process is biased, then all of a sudden it doesn't represent the population we're sampling from. It's representing something else, some other population with these frequencies. Now the real general population hasn't changed, it's just that our sampling process has changed to alter these frequencies. And that's why bias is such an issue, because depending on what you're sampling, it may cause massive ripple effects. But you can see that the only way E of x is equal to E of x bar is if your sampling process has no bias. What will the new E of x bar be? Well, under the biased one, E of x bar will now be equal to this value, if I remember correctly. Yeah, 7.5, $7.50. So this is the new X bar. So if you sample incorrectly, sure, you're generating all the outcomes are exactly the same, but the way you experience these outcomes is not the same. And all of a sudden you have a very different E of x bar, and it doesn't equal E of x. And the whole purpose of sampling is to understand this value, the true mean of the population you're sampling from. But if it's biased, if your sampling process is biased, all of a sudden these two don't line up. So sure, you have a sample, but it doesn't give you any idea of what the real distribution is like. So what is the only way that E of x bar equals E of x? Is if sampling process is unbiased. That's it. There's no other way that can happen. And just to do one very simple outcome, 70, you'll notice in my simulation, I got 70, an average of 70. That under unbiased situation should only be happening 1 out of 1,000 attempts, so tens, hundreds, thousands. That's how often I'll get an average of 70 under unbiased conditions. But I biased it. I went from 10% to 20%. So the chance of getting an average of 70 has now been altered, 20%, third. So now it happens 8 times out of every 1,000 attempts. Again, it's very unlikely, but you'll notice by chance it did happen. The point is that all of a sudden I've altered these probabilities are no longer the same, and they don't match the original set at all as far as the means. So we sample in such a way that the means of these two groups are the same, and you can only do that through sampling process that's unbiased.